Welcome back to AI Paper Podcasts. We're the place where we crack open the latest and most intriguing research papers in AI and tech. Today, we're dissecting a paper that's really, I think, pushing the boundaries in robotics. It's called SimpleVLA-RL, Scaling VLA Training via Reinforcement Learning. This is a deep dive that genuinely expands our understanding of what robots might be capable of. So maybe first, for those looking for the quick takeaways, let's just summarize why this paper is getting attention. We're looking at vision language action models, VLAs.
Right. The ones that let robots see, understand commands, and then, act.
Exactly. They're incredibly powerful, but traditionally they've hit these two major walls. First, there's a severe lack of that expensive human-operated data needed for supervised training.
The SFT data, it's a real bottleneck.
And second, they often struggle to generalize. Taking what they learned and applying it to new tasks or slightly different environments.
Yeah, that generalization piece is critical.
Okay, so the breakthrough here is this thing called SimpleVLA-RL. It's presented as a really efficient reinforcement learning, or RL, framework, and it seems to dramatically enhance these VLA models. We're talking about a system that apparently slashes the need for huge data sets.
Yeah, the paper claims it works wonders even with just one demonstration per task in some cases. That's pretty remarkable.
Right, and it achieves state-of-the-art performance. It outperforms traditional SFT and other baselines on tough simulation benchmarks like Libero and Robotone.
And importantly, it shows promise transferring to actual physical robots, too.
Plus, it boosts that generalization we talked about across different setups, objects, tasks, areas where SFT tends to, overfit and fail.
And then there's the really cool part.
The pushcut thing.
Exactly, this pushcut phenomenon. The robot basically discovers entirely new, more efficient ways to do things, actions that were never in its training data.
So it's not just learning to copy, it's inventing.
In a way, yes. It's finding more optimal solutions. So this isn't just a small step. It feels like a fundamental shift.
Showing how RL can unlock, scalability, adaptability, maybe even a kind of creativity in robots, paving the way for more robust autonomous systems. Okay, so that's the nutshell. Now, let's really unpack this. What exactly makes VLA models so challenging to scale up with the old methods? And why is RL suddenly looking like such a game changer here?
That's the perfect place to start. So at a high level, these vision language action models, VLAs, they're trying to give robots this comprehensive understanding of their world. They bring together visual perception, seeing what's around them.
Like cameras, depth sensors.
Exactly. Then language understanding, so they can take instructions like stack the red block on the blue block or put the bottle in the bin.
Natural language commands.
Right. And then, the crucial part, action generation. Turning that understanding into physical movement, manipulating objects. The goal is really intelligent, interactive robots.
And the usual way to train these, it often follows the large language model playbook, doesn't it? Like a big pre-training phase, then fine-tuning?
Precisely. You start with massive multimodal data sets, maybe internet videos, image-text pairs to get a broad understanding. Then comes the supervised fine-tuning, the SFT. That's where you use high-quality, specific robot trajectories, usually human teleoperated, to hone the robot's skills for particular tasks.
Okay.
But that SFT phase is exactly where the big problems pop up when you try to scale things.
Right. You mentioned the bottlenecks.
Yeah, the first one, and it's a big one, is data scarcity. Just think about how hard and expensive it is to collect lots of good human-operated robot data. You need carefully designed setups, lots of different objects, skilled operators guiding the robot perfectly. It's painstaking.
It's not like scraping the web for text data.
Not at all. It's a major bottleneck, limiting the scale and diversity of data we can actually get. Lots of recent papers point this out.
So getting enough data is hard, and getting the right kind of high-quality data is even harder and more expensive.
Exactly. And that scarcity directly feeds into the second challenge, poor generalization. Because these SFT models are trained on relatively limited, often very specific data sets.
Tied to certain scenes or certain tasks.
Right. They really struggle when you take them outside that narrow training distribution. Give them a task that needs combining skills in a new way, or a really long sequence of actions, or put them in a real-world setting that looks slightly different.
Performance drops off a cliff.
Often, yeah. They tend to overfit to the specific examples they saw during training. They learn the demos, but not necessarily the underlying skill in a robust way.
Okay, this sets up the core question nicely. We've seen RL do amazing things for large reasoning models, like DeepSeek R1, boosting their abilities using just outcome rewards. Did it work or not? So the question is, can RL bring that same kind of leap forward to VLA models for their step-by-step physical action planning? Can it help them break free from needing perfect demos and generalize better?
That's exactly the thinking behind SimpleVLA-RL. The paper positions it as an effective RL framework specifically built to tackle these VLA challenges. It's about extending that RL success from reasoning into the messy physical world of robotics.
And it's not starting from zero, right? You mentioned it builds on existing work.
Correct. It builds on a framework called VRL, which stands for Volcano Engine Reinforcement Learning, originally developed for LLMs.
Whoa.
But, and this is key, applying RL to a robot interacting with the world is very different from an LLM just outputting text.
Yeah, the interaction part seems way more complex. Consequences are real.
Totally. The environment is dynamic, sampling actions takes time, maybe even breaks things. So the paper details some really crucial VLA specific adaptations they had to make.
Like what?
Well, for instance, VLA models need interactive trajectory sampling. Unlike an LLM spitting out tokens, the robot acts, the world changes, it perceives again, acts again. It's a multi-round dialogue with the environment.
Right, it's not a one-shot generation.
Exactly. And because robot interaction, even in simulation, can be slow, they needed scalable parallelization. They used multi-environment rendering to run many simulations at once, speeding up data collection massively.
Smart. Generating experience faster.
They also optimized the loss computation specifically for this setup and bundled everything into an integrated training inference rendering framework.
So it's a whole system designed for efficient robot RL.
Yeah, these aren't just minor tweaks, they're significant architectural changes needed to make RL practical and effective for embodied agents like robots.
Okay, that sounds like some clever engineering. So drilling down a bit, what does this actually mean for how the robot learns? Can you walk us through the mechanics? How does SimpleVLA-RL actually implement RL for a VLA model?
Absolutely. Let's break down the RL formulation they use, component by component. First, you have the robot state. Let's call it A state time t. This isn't just one thing, it's a mix of input.
Multimodal, right.
Exactly. You've got visual input, maybe camera images, maybe depth info. You've got proprioceptive data.
That's the robot's sense of its own body, like joint positions.
Precisely. Its joint angles, the position of its end effector, things like that. And crucially, you also feed in the language instruction for the task it's supposed to do.
So it sees, feels, and understands the command all at once.
Right. It's a holistic snapshot. Here's the world, here's where I am in it, and here's what I need to do. Okay. From that state process, the VLA policy then decides on an action at
The actual command sent to the motors.
Yeah, like move the gripper slightly left or set these joint angles. The paper mentions using different decoders, like a diffusion expert or an action tokenizer.
Action tokenizer. So discrete actions.
Kind of. It represents actions as distributions over possible action tokens. This is important because the RL algorithm they use, which is like PPO, works well with these probability distributions over actions. It allows for exploring different possibilities.
Okay, state leads to a probabilistic action. Then what?
Then comes the environment. The robot performs the action at, and the environment, whether it's a simulation or the real-world updates. It transitions to a new state, +1, and critically, the environment also provides the reward signal.
The feedback signal. Is it complex, like you got closer?
Can be. Often people design intricate process rewards for things like distance to target or reaching intermediate steps. But a key design choice here, aiming for scalability and simplicity, was to lean heavily on a simple binary outcome reward.
Did it work or not?
Pretty much. 1, if the task was successfully completed at the end of the trajectory, 0 if it wasn't. This reward is then propagated back to all the action tokens within that trajectory.
That seems surprisingly simple. Why just success fail?
Because it's incredibly scalable. It applies to any task without needing careful manual reward shaping for each one. Handcrafted process rewards often don't transfer well to new tasks or environments. This simple outcome reward avoids that whole problem. It just cares about the final goal.
Okay, that makes sense for scaling. Simple and universal. So the robot interacts, gets states, takes actions, gets a final reward. How does it generate a whole sequence?
Through rollout. The VLA model doesn't just predict one action, it engages in continuous interactive sampling with the environment. At each step T, it takes the state set, samples an action chunk from its policy, the robot executes it, the environment updates to ASTAP +1 and gives a reward, which might be 0 until the end, and the cycle repeats. This generates a full trajectory of interaction.
Got it. So it's constantly acting and reacting.
Yeah.
Now, you mentioned RL needs good exploration. How did they boost that, especially for tricky robot tasks?
Right. Exploration is super important. If the robot just keeps doing the same slightly wrong thing, it won't learn. They used a few techniques. First, dynamic sampling. Sometimes in RL, especially with sparse rewards, you might get a whole batch of trajectories where the robot fails every time. Or maybe it succeeds every time.
And then the learning signal flatlines.
Exactly. No difference between trajectories means no gradient, no learning. Dynamic sampling makes sure each training batch has a mix of successful and unsuccessful trajectories. It keeps sampling until it gets that mix, which keeps the learning signal strong and stable. They cited this being effective in LLM-RL, too.
Okay, so ensuring variety in the outcomes. What else?
Second, they tweaked the clipping range in the GRPO objective. GRPO is a variant of PPO, a common RL algorithm. They changed the range from the standard 0.8, 1.2 to 0.8, 1.28.
Seems like a small change, 1.2 to 1.28.
It seems small, but that slightly larger upper bound allows the probability of initially low probability actions, maybe weird but useful exploratory moves, to be increased more significantly during an update step. It gives more room to boost promising unexplored actions.
Encouraging more exploration of less likely but potentially good action.
And precisely. And third, they used a higher rollout temperature. They cranked up the sampling temperature during trajectory generation from 1.0 to 1.6.
Making the action choices more random.
More stochastic, yeah. Less greedy, more diverse. This pushes the robot to try a wider variety of behaviors during exploration. The paper actually shows this gave them noticeable bumps in performance, like 10-15% gains.
Okay, so dynamic batches, wider clipping, more random actions, all pushing for better exploration. And the training objective itself.
They used a modified GRPO objective. The main tweak was removing the KL divergence regularization term.
What does that do?
The KL term usually keeps the updated policy from straying too far from the previous policy iteration, promoting stability. Removing it does two things: reduces memory usage and speeds up training because you don't need a separate reference model.
And presumably lets the policy explore more freely.
That's the idea. By removing that constraint, it potentially allows for larger, more exploratory policy updates.
So a lot of interconnected pieces designed to make RL work effectively and efficiently for these complex robot tasks.
Exactly. It's a carefully engineered system.
All right, we've got the theory and the mechanics. Now let's get to the results, the experimental validation. You mentioned the paper shows SimpleVLA-RL doesn't just help a bit, it also significantly outperforms the baseline methods.
Indeed. The proof is definitely in the pudding here. They tested it rigorously on several well-established robotics benchmarks. You've got Libero, which has a good variety of language-guided manipulation tasks. Then Robotone 1.0 with 17 bimanual tasks, and the bigger Robotone 2.0.
Robotone 2.0 sounds tough.
It is. 50 tasks, over 700 object instances, strong domain randomization meaning lots of visual variation to test robustness, and tasks ranging from short to extra long sequences of actions. Plus, they did real-world tests too.
The ultimate test. So comparing standard supervised fine-tuning, SFT, against SimpleVLA-RL using the OpenVLA model as the base. What did they find?
The improvements were pretty striking. On Libero, the average success rate went from 91% with SFT up to 99% with SimpleVLA-RL.
Wow, 99%. That basically means it solved it, right? And better than other models.
Yeah, it surpassed other strong baselines like Zero and UniVLA. And on the harder Libero long tasks, the ones requiring longer sequences, it jumped from 86.5% success with SFT to 98.5% with RL. That's a solid 12% absolute gain.
Okay, impressive on Libero. What about Robotone?
On Robotone 1.0, they saw a 30.6% absolute gain over the SFT baseline, going from about 40% success to over 70%.
It's a huge leap.
It is. And on the more challenging Robotone 2.0, the relative improvement was around 80%. SFT got 38.3%, but RL pushed that up to 68.8%. Again, significantly better than other methods like R0 or RDT on that benchmark.
And this held across different task lengths.
Consistently, short, medium, long, even the extra long horizon tasks saw gains. They mentioned specific tasks like blocks rank RGB improving by 11%, put bottles dustbin by nearly 19%.
And the kicker is, this was without more demo data.
Exactly. That's the crucial point. All these gains came from applying RL on top of the existing SFT model without needing a single additional human demonstration.
Okay, this is where it gets really impactful, right? This isn't just about benchmark scores. It's about tackling those fundamental problems we discussed earlier. This matters to you, the listener, if you're thinking about actually deploying robots.
Absolutely. Let's talk about the implications. First, overcoming data scarcity. This is huge. They did this experiment. What if you train the initial SFT model with only one single demonstration trajectory per task suite in Libero? Just one example.
Okay, that's extreme data scarcity. How did SFT do?
SFT alone was, well, not great. Average success rate of about 49% and only 17% on the long horizon tasks. Really struggled.
Makes sense. Not much to learn from.
But then they applied SimpleVLA-RL to that same one trajectory SFT model. The average success rate across Libero shot up to nearly 97%.
Wait, from 49% to 97% with just one initial demo.
Yep, and get this, that 97% success rate beat the performance of the SFT model trained on the full data set of 500 demonstrations, which only got 91%.
That's incredible. So RL bridged the gap and then some.
Exactly. On the Libero long tasks, it went from 17% to almost 92% success, a massive 74% gain.
What does that tell us?
It tells us that RL, with its trial and error exploration guided by simple outcome rewards, can compensate massively for a lack of expensive demonstration data. It can figure things out on its own, which is critical if we ever want to scale robotics beyond tasks where we can afford hundreds of perfect demos.
Okay, data scarcity tackled. What about generalization? The other big SFT weakness.
They looked into that specifically. SFT models often suffer from catastrophic forgetting. They learn the training tasks, but if you test them on a slightly different unseen task, they just fail. Performance can drop to 0.
Because they overfit to the training distribution.
Exactly. They tested this by training on 9 tasks and testing on one unseen task in Libero, varying spatial setups, objects, or goals. SFT often failed badly on the unseen tasks. SimpleVLA-RL, however, consistently improved performance on these unseen tasks. Gains of 5-15% on unseen goal tasks, even a 36% gain on one tricky unseen object task.
So it learns more robust, transferable skills.
It seems so. It manages to learn the new things from RL exploration without forgetting what it learned before, and applies it more broadly. It learns more generalizable strategies.
Okay, that's huge for real-world adaptability.
Right.
Which brings us to the real-world tests. Simtoreal. How did that go?
This is always a critical hurdle. They use Agilex Piper robot arms, testing tasks like stacking bowls, handing over blocks, picking bottles, clicking a bell. And the key constraint, the models were trained only in simulation. No real-world demos were used for training at all.
So pure Simtoreal transfer. How did RL help?
It helped significantly. The average success rate across these real-world tasks jumped from a 17.5% for the sim-trained SFT model to 38.5% after applying SimpleVLA-RL in simulation. It also outperformed another method, RDT, which got 23.5%.
Doubled the success rate, basically. Any specific task examples?
Yeah, Stack Bowl saw a huge relative jump from 32% success with SFT to 70% with RL. That's a 96% relative improvement. And even on Pick Bottle, which needs high precision and where the SFT model completely failed, 0% success.
Which happens a lot in robotics.
Right. RL managed to get it to 15% success. Still not perfect, but going from 0 to non-zero on a hard precision task purely through Simtoreal-RL is quite promising.
Definitely. It shows that RL training and simulation can meaningfully improve how robots perform in the actual physical world, offering a potentially much cheaper way to develop robot skills.
Exactly. It makes the prospect of scaling real-world robotics seem much more feasible.
Okay, now for the part that really caught my eye, this pushcut phenomenon. It feels like more than just improved performance. It's like the robot got creative.
Yeah.
Tell us about that. It's genuinely fascinating.
It really is. It's one of those results that makes you pause and think. So imagine tasks like move this can to that spot or place object A next to object B. The human demonstrations they used for the initial SFT training all used a standard grasp, move, place strategy. Pick it up, carry it over, put it down.
The intuitive way most people would do it.
Right. But the model, after being trained further with SimpleVLA-RL, started doing something different on its own. Instead of grasping the object, it learned to simply push it across the table to the target location, a pushcut.
Like a shortcut, but using pushing. And this wasn't in the demos.
Not at all. It autonomously discovered this strategy. The paper has figures showing it. It's more efficient in some cases, fewer complex steps.
That reminds me of the aha moments they talked about with large reasoning models finding novel proofs.
It's a very similar concept applied to physical action. It perfectly illustrates the difference between SFT and RL. SFT learns to replicate the patterns it sees. It copies the human strategy. RL, driven by the outcome reward, did the object get to the target? Doesn't care how it gets there, as long as it does.
So it explores different ways.
And if pushing works and gets the reward, maybe even faster or more reliably than a complex grasp, it learns that pushing is a good, valid strategy. It's not constrained by the correct procedure shown in the demos.
It's optimizing for the goal, not the process. That is a form of robotic creativity, discovering novel solutions.
It really feels like it, finding solutions beyond human demonstration.
Okay, it sounds almost magical. More efficient, more general, even creative. But surely there are limits. When does SimpleVLA-RL struggle or fail?
You're right, it's not a magic wand. The paper is quite clear about the limitations, particularly the importance of the initial model capability, meaning RL needs something to build upon. If you start with a base SFT model that has literally 0% success rate on a task, it never even accidentally does anything useful, then RL fails completely.
Why?
Because if it only uses outcome rewards, success fail, and every single trajectory it samples during exploration results in failure,
Then every trajectory gets a 0 reward.
exactly. There's no positive signal, no gradient, nothing to tell the model that thing you did was slightly better. Learning just stalled. It can't bootstrap itself from absolute 0 competence using only outcome rewards.
So it needs at least a tiny spark of initial success.
Or at least some task-relevant behaviors it can explore from. There seems to be a performance threshold. They showed an example, pick dual bottles, where the initial SFT model had only a 1.2% success rate. Very low.
MRL.
RL only managed to improve it marginally to 4.3% because the initial foothold was just too weak for exploration to reliably find successful paths and get meaningful positive feedback.
So better the starting point from SFT, the more RL can potentially improve it.
Yes, there's a clear correlation shown in the results. A model starting with 100 demo trajectories, maybe 7% success, gained 18% from RL. A model starting with 1,000 demos, maybe 28% success, gained over 22% from RL on the same tasks. Stronger start, bigger RL boost.
Okay, that makes sense. So RL isn't a replacement for some initial capability, but it's incredibly powerful at amplifying and refining that capability, especially when data is scarce or generalization is needed.
That's a great way to put it. A minimal level of competence is essential for RL exploration to be effective.
Right. So bringing this all together, this deep dive into SimpleVLA-RL, really paints an exciting picture for the future of VLA models, doesn't it? It hits the data scarcity problem hard, making those costly demos less critical. It massively boosts generalization, letting robots adapt better. It shows real promise for Simtoreal transfer. And maybe most intriguingly, it reveals this potential for robots to discover genuinely new creative behaviors like the pushcut, finding solutions we didn't explicitly teach them.
Exactly. I think this work really underscores that RL isn't just some minor fine-tuning add-on anymore. It feels more like a fundamental paradigm shift for robotics. It could be the key to unlocking truly autonomous, adaptable robots, ones capable of exploring, learning, and maybe even discovering solutions to problems in ways we haven't even conceived of yet. It really makes you wonder, as these techniques get better and we apply them to more complex, open-ended scenarios, what other unexpected emergent behaviors or strategies might future VLA models uncover?
A truly provocative thought indeed, and definitely leaves us excited about what's coming next in robotics and AI. Well, thank you for joining us on AI Paper Podcast in this deep dive. If you, the listener, want to explore further, definitely check out the original paper, SimpleVLA-RL, and the associated Prime-RL, SimpleVLA-RL GitHub repository. They mentioned it was released around May 2025. We'll be back soon with another look into the latest in AI research. Thanks for tuning in.